All right, here we are. We're in our GY 101. It's the first day of October. I think you're about a quarter of the way through already. Isn't this wonderful? So I'm Mark Olson. I taught this course for a couple semesters and lectured in this course for several lectures before that, quite a bit of the time. I'm an old dude. I graduated from Montana State a long time ago, chemical engineering. Came here to Missoula to work in the pulp mill. Started out as we had a grant from the EPA to study emissions from some new or retrofitted emissions control equipment. And that was a 9-month grant and never left. I worked out there for 37 years. It closed about 5 years ago. And that closure brought me here to this program because we got training assistants and got medical out of it when we went. So I did that, and there were quite a few guys in the mill doing it at the time. Not too many in this program, a few. Graduated, and I was consulting a little bit and substitute teaching high school, which I really enjoyed. My last years at the mill, I was doing quite a bit of training. I kind of got into doing this kind of a thing. And like I say, started lecturing for Brad off and on as he needed help, and then had the course the last couple of years, and budget cuts have kind of mandated that there's fewer adjuncts, and so I'm not doing it full time now. I just may be the only lecture I do, so thank you. I appreciate it. It's
Did you
fun.
Work with Laura Kosmolsky?
The cause, yeah.
Okay.
Yeah, I did.
Right.
Yeah. You know where you know her from?
Yeah, I've known her for
Okay.
years.
Where's she?
Where?
Yeah.
She's
She around Brazil still? Something
Yeah.
she changed. She was a
university, and then
the boiler
now
plant.
she's just working on her own,
Yeah.
consulting.
Yeah, a lot of people out there. That was, good thing I'm not talking about bioenergy today and trees and wood. I can get off on that a little bit. I know a lot about. That's quite a process out there. And one thing that some people don't think about is the fact that that facility at one time had 700 people employed. It was maybe 500 the last few years, but that brought money in from outside this region. Outside the city for sure, outside the state for sure, outside the region. And you get a place like that closed down, there's others. You don't have money coming in the community anymore. It's a lot more of us trading dollars. There's other things, other good things too, but that was a lot of money coming in the community. It's tough when something like that happens, and the reason we got closed down, can't get the wood. In the later years we started out mostly wood chips from sawmills, and of course that was ending. And we built our own chip plant, and we were chipping on our own logs 24 hours a day. And those logs are coming from friggin' Wyoming, South Dakota, many of them, some Montana. And you saw where the St. Regis lumber facility is going back to one shift, 90 people or something, and it's logs, can't get them. And I don't know. You don't know why policies are, why they are, and we can argue. You can't get in the woods to get them. And we talk about a carbon, reducing our carbon footprint. Trees are, if sustainably harvested, and a big if on that, sustainably harvested, are carbon neutral. You could make energy out of trees. You can make pulp out of trees. We had the energy from the mill powered the mill, but it also powered about 30% of our own electricity. So the off steam from processes would be used in other part of processes and whatnot. And the organics from the wood went into heat too. And the inorganics went into the cellulose went into the paper, but the other went into the wood. It wasn't perfect, but that's as far as I went too far there probably, but it's a wonder. I'd like to see it turning the other way a little bit in the right way. I'm not one to want a bunch of clear cutting out there either or whatnot, but my God, we got them burning up around us. We're breathing it anyway. I mean, why can't we control how we harvest it? Divert some of the billions of dollars that go to fighting fires to harvesting in the right way for the right uses. It might not be pulp and paper.
Well, it would be so nice if we could figure out an efficient way to harvest all of the dead trees
Yeah.
throughout the entire state from beetle kill and everything else. That
Well,
needs to
some
be
talk, you
harvested without
can't,
clear
yeah,
cutting.
yeah. Well, we had some contracts late in our tenure that were just that, beetle killed. With, you know, within 3-4 years of their death, trees are still good. They're still good for lumber. They're still good for pulp and paper.
Standing seasons.
Yeah, yeah. So anyway, I got off on that a little bit. So this is yours. You know, all of you, thanks for coming. If I get off, there I went. I got off already. Keep me to about 20 minutes a segment. Somebody be a timekeeper for me. 20 minutes to half an hour, and then cut this video off so you don't go brain dead trying to watch it. But your questions, I want to interject anytime your questions, something you want to bring up. I might not be able to entertain them all because I'm not around it, you know, day to day like I was last semester. We're going to have a sample problem we're going to work on, and then we'll get into some lecture from the text or from anything you want relating to the subject matter. Okay, so. Any questions right off the get-go? And again, if you think of something something going on you want to know about, let me know. Let's see if I can find see, this has been an issue so far already. A lot of practice. There. Maybe that's the way I've got to do it. Yeah. Well, I might have it already up here. There we go. Here's a sample problem, and don't get freaked out by number 3. I'll help you if you have not heard of the term capacity factor. And as I showed in my introduction there, I think Dr. Layton goes there early on that one difference may be from this curriculum in class from some of the others you may do. There's a pretty big attempt at trying to put quantities to what we're talking about here. Let's put quantities to it, and let's learn how we can do that when we hear about something. That's why I'm so adamant about these problems, as some may remember. So here's a sample problems, and can you read that? Okay, let me read it real quick. A little bit of baloney, but so we got a bunch of rail cars of coal rolled through here all the time. Well, how much energy is that compared to other things? You know, what are we up against? And I wanted to determine and these numbers are very, very generic. You could be off 25, 35, 40% on some of these factors I've presented here, okay, because they're very generic. You know, a lump of coal is not a lump of coal. You saw it probably in your lecture Tuesday. Different qualities of coal, very different, you know, and from where it's mined, deep, shallow, how much energy it's got, how much sulfur it puts out, how much electricity you can get out of it. So these are very, very generic, but it's for the purpose of demonstrating how one can kind of take a visual and get it into some kind of numbers and get a number from another visual and compare. And what I wanted to do was let's compare the amount of electricity you can get from coal to the amount of electricity you can get from a typical, and typical is very generic, solar system and a typical wind turbine generator. Okay, we've got all that in Montana. So a typical rail car of coal holds approximately 200,000 pounds of coal. From our text, we know that the typical heating value of coal is 28 gigajoules per metric ton, and we'll look at a table and you see that that varies a lot. And coal energy to electrical energy efficiency is approximately 30%. So if you're taking so much coal energy and you're burning it like they do in a coal strip and making electricity out of it, it's generally 30% efficient. I think that might include transmission losses. It doesn't make a lot of difference to this analysis. I think the coal-fired boiler people will tell you it's a lot more efficient than that, but with modern boilers. So our first question is, so one of these rail cars of coal, how much electricity can that produce? Period. That one rail car or coal. Let's go one place first here. That's another learning thing. And just stick with that one problem for now. And again, I warned you, and this is done on purpose, because that bothered me in this course forever when I first started with it. I'm an engineer out the mill forever, manager and whatnot, and we always had projects. We looked at we spent millions of dollars on energy, so we looked at it really hard. But I was always looking at things in U.S. units. I come to this class, and the two techs, I think they're wonderful techs, what are they in? You know? Holy cow, have I flown to England or something? It's driving me crazy. Well, you go down I'm thinking about a distance. I think about feet. I don't think about meters, so I've got to find a way to, relate. And here we've got 200,000 pounds. This is our U.S. pound. This is not anything metric. When we solve these problems in metrics. So I think the thing to do is take any U.S. units, convert them to metric, solve the problems in metric, because that's the way the book does it, and then you can convert the answer back to a U.S. unit if you want to, for comparability. In this case, you don't have to, because you're comparing electricity, which is measured, or the naming convention or the measurement's the same in either country. But let's go to one little thing here first. I'm doing okay getting there. And I don't know how far they've gone on any of this in the class. Lecture names, where's my, there it is. Remember these icons. So, let's go to the next page. There we go. I got you. What's the difference between, where are you at, dude? Might drive us all crazy by the time we're done. There it is. Jesus.
Want the answer now?
What's the difference between power and energy? What is energy and what is power? Have I gone through that much with you? It's fundamental to the course. It really is. It's and you go to read about renewables, read about energy, and what you read sometimes treats those two terms as the same. They're not. They're not. So,
Power is the rate at which energy is used.
yeah. Power is the rate at which energy is used. God dang, get this thing to right. So energy, this thing is not very good, but energy is a quantity. Okay? Power, do you read that at all? Is a rate. Good, thank you. Okay, so energy is force times distance, right? Same as work. Whereas power is energy over time. Look at this thing. There we go. Hey. Hi, I'm Mark.
I'm Joseph.
Okay, I'm filling in. There's a sign-in sheet there, so I'll visit you with it when we get onto a break.
Okay.
Don't worry about it. Get caught up, and yeah. We're just getting started. I showed a sample problem up here, and I'll get back there in a second.
Okay.
And I've already diverted it a little bit. But this is fundamental to the understanding of energy and power and the quantification thereof. Force is mass times acceleration. Force is okay. Energy is that force over distance, all right, in physics. And I think that was probably covered in the first chapter or two. But there's a basic difference between the two. And energy is a quantity. It's joules, megajoules. What are some other quantities? Kilowatt hours. Whereas power is a rate. Power is kilowatts, okay? and power as energy over time. These lights, let's say there's 100, these aren't it, but 100-watt light bulb overhead. Okay. When it's running, it uses 100 watts of power. It's not using 100 watts of energy. Energy is the power times time. That's just, and that's the equivalent of power is energy over time. So that 100-watt bulb, if it ran for 3 hours during the 2 lectures today, would use 300 watt-hours of electricity. Not power. Its power usage is 100 watts. Big difference. As you get into these kinds of comparisons of our basic fossil fuel sourced electrical production, energy production, our cars, the energy and power, it's fundamental to to this curriculum to understand the difference, to understand what is being determined or what's being talked about, what is being talked about, the difference between the one and the other. And it's not always easy sometimes. It's not always easy sometimes. Okay? We there? I got off there a little bit, but this is very fundamental, and we'll get back to that problem. Okay, so there's a sample problem. So in number 1, that one rail car of coal, and we're given the parameters for that coal rail car, would produce how much electricity? It wouldn't. If you're going to give the answer as kilowatts, you're not going to give the right units. We're talking kilowatt hours or megawatt hours or whatever. Whereas a wind turbine, for example, can produce, one turbine, let's say 1.5 megawatts. Well, again, there's no time with it. So that's power. That turbine, when it's at max capacity, the wind's right, is producing 1.5 megawatts. If it ran 1 hour at that capacity, it produced 1.5 megawatt hours of electricity. Real differences there. It's fundamental to the program to understand that. As much as I worked around energy, I had the boilers for a long time out that mill. I had the electrical distribution system, the turbine generators. I don't know if I fully understood that until I took this course. And you go to read something in the paper about the UVM boiler that didn't make it, or about what's the latest one, coal strip, and what's going on. A lot of times they treat those two terms as the same. They're not. Okay. Right. So if what's one thing you get out of this course is that understanding. And as I taught this course early on, I wasn't emphasizing it, and my boss's boss, old Doc, come into a few classes and started asking questions about the difference between power and energy, and halfway through, a lot of students didn't know. So just about every class, every other class, I delve into it just a touch. Okay, I don't know if they've already done that or not, and I hope I'm not covering ground that's been covered, so you're just about ready to throw up about it. But I got it. Okay. So we'll go back. Any questions on that? And of course, there's a lot of other units to do. Now, this first problem asks this one rail car of coal weighing 200,000 pounds, and we're going to assume that that coal has a heating value of, as written. How much electricity can that produce? Okay, work on that a little bit. And the appendices in your book, as Rain will remember, I'm really big on using those. Don't go Google a bunch of stuff, please. I had one student 2 semesters ago, man, he got it right most of the time, but he'd get off base because he'd be Googling the wrong thing. Yeah, those appendices are great. You can get to about anywhere you want to get to using the relationships in the appendices. And I'm huge, as we go through this problem, with word problems, the first thing you want to do is write down what you're supposed to find with the units and write down what you're given with the units. Okay? And a lot of times that will kick you into gear looking at the units required in your answer and the units you're given to work with. Okay? So let's go there. Do you want to work on that for a minute? Is that what he typically does? Yeah, why don't you work on
Give
it?
us a little bit to work on it.
Yeah, do that. Just work on that first one, and if you get towards that second one, that's fine too. I will say there are several of these problems, or at least one that's got more data in it than you need, the second one.
Wow.
Can you make that larger? Can you see it well enough? Okay, good.
Coal is so much more energy dense than those panels, it's ridiculous.
Yeah, and we'll talk about it a little bit. It's the full treat scene needs to go another place too, but we don't have time for that. Do that right. I'll pick it up. You're all right. I hope that microphone is running. So the first thing to do may be to calculate the amount of energy in that coal car, separated into different parts. How many joules, how many joules, megajoules, or gigajoules, whatever term you want to use, of energy is in that coal car? Okay, because you're only given how much that coal weighs net in that coal car and the heating value of that coal. But from those two terms, you can calculate how much total energy is in that coal car. Energy is a quantity. Okay, let me get to a new page already, in case we come back to this one. There. Okay, the first problem, number one, if I can get this thing to work again. Yeah. Not very good though. God, how come? Oh, there it is. Okay. That number one, what are we to find? Electricity, right? And what would be the units? As?
Kilowatt hours.
Kilowatt hours per rail car. Boy. Can you read that? Okay. And what are we given? Car weight, right? Not the car weight. Car's coal weight, there's a difference, as 200,000 pounds. And the coal, I'm going to abbreviate that, heating value, right, as, what was that, 28 gigajoules per what?
100 metric tons.
Per metric ton. Exactly. Perfect. So we've already got an issue going on here. We're given pounds, US pounds, and metric tons. So we got to take and find out how many tons are on that car first, right? Who's done that? So the car coal weight is the 200,000 pounds. How far you want me to go with this? How do we convert pounds to metric tons?
Divided by
Okay.
tons.
Okay. What's the conversion? That's 200,000 pounds per car.
2,240.
Okay.
Equals
Gosh, I can't get this thing. Excuse me a second here. There it is. So you want to divide it by?
Yeah. The 2,240.
Okay.
Works out to be 89.28 tons per real car.
Yeah, you're
About
close.
89%.
Yeah, I got 90, but that's okay. So 2240. What's your conversion there? Kilograms or
Metric tons.
metric tons?
That's for American tons, not English tons.
Okay.
Metric tons is 2,205 tons.
Well, let's look at the appendix. They give a number of different conversions. Okay. Let's go there.
It doesn't give metric tons in pounds, so it's 2,205.
Well, because I looked it up, and then it was like,
You're pretty close.
Yeah, 2,000.
yeah, so I guess it depends on.
If you convert it to kilograms, it might be
Yeah.
200,000 pounds times 0.534.
There you go. And there's many different ways of getting there, but that's the way I went there. So let's continue that way. Sorry. But you could divide it by 2205, and I thought that's where you were going, but you were
Yeah.
going a different place. Yeah. Yeah.
I went that way.
Yeah, no, well, we got to make sure we get and I'm adamant about when you write these problems out, when I was teaching, you had to show your units to get full credit. And I'll tell you why. You're going to get a lot more stringent problems going down the road if you stay in this program and some of these other classes. Brian Kearns and particularly energy storage with Fraser. Oh, you got to show your units because and I did it all the time. You'd be thinking you're solving kilowatt hours, you didn't convert megawatts to kilowatts because you just didn't write it down. You got fast with it, or I got fast with it. So now I got to find where I'm at here. This thing. Hopefully this is not. What I did before is not working. Come on. There it is. Okay. Let's scratch that. Okay. Let's go times the point, what is that, number 4? See, I can never remember the numbers. There's some I remember. But with metric, I don't remember those very good. Kilograms per pound. Okay. Jesus. Times. So now we've got it in kilograms, right? The pounds cancel out. See that? And we want to get it in tons. How many metric tons per kilogram? No, you're back at the gigajoules. How many metric tons per kilogram? Yeah. Oops. How come I'm not getting this? Yeah. That gives us, okay, the pounds cancel out, the kilograms cancel out. That gives us the tons, okay? So it's about 200 times 0.54, yeah, 90? It's about 90 tons. Rain got 89, is close enough, we'll call it 90 in this one. So that's 90 tons per car of coal. Okay? Now if we got 90 tons, we should be able to calculate how much electricity. Right? I didn't write down another one of the
You
givens.
multiply that times your 28 gigajoules,
Yeah.
and then do your conversion from gigajoules to kilowatt hours.
Did I have the, yeah, yes. And there's one more thing you need to do. The coal-fired plant is 30%. There you go. And I didn't write it here. See, there you go. I've already skipped one of the
Was I
givens.
wrong in that when I did it, I took 30% of what the gigajoules was before I then completed it?
It doesn't make a
Same
difference.
thing.
You're fine. You're absolutely fine. Yep.
I just figured I'd do that before the number
Yeah.
got ridiculous while it was still manageable.
Yeah, yeah. You're fine. There it is. So we got our 90 tons of coal. You read that? Probably not. Per car. Every number has a unit unless it's a ratio, all right, or a factor. And every unit has got two components to it all the time. Okay? 5 shirts. Well, 5 shirts. I use 5 shirts per week, per day, per year, per lifetime. Okay? I lose 6 golf balls. How long do they last me? There's every number. You don't, and a lot of times they're assumed in the denominator. When you get into these kind of problems, you're going to want to include that denominator all the time. Even here, I forgot. We've got 90 tons we calculated, but it's 90 tons of coal per car. Okay. Oops, about ready to lose this. Got it already way back here. Okay. Some of you have already got there. So let's, okay, we'll take it times 28 gigajoules per ton times our efficiency. So that means that all that efficiency is the energy out divided by the energy in. And I don't know if you've had that prior now or not, you probably have. That's all that efficiency is. And it's very, very generic to say it's 30% efficient, the coal-fired boiler, all the way through the turbine generators to the electricity coming to you is 30%. But it's a reasonable number. Okay, now we got our coal, tons are out of there. We're into gigajoules. What's another factor we need to have? Okay. In your appendix, there's one of the more useful things you'll find in this. Look at table A5, page 626. You probably already run across this with some other analysis that have been done. A joule, megajoule, that's an energy unit. That's a quantity. A kilowatt's a power unit. A megawatt's a power unit. Kilowatt hour, that's energy. And somewhere in your text, this number is derived. It's given in the appendix because it's so useful. It's just a time factor over that energy, but it's 3.6 megajoules per kilowatt hour. Okay? That relationship, we can get our answer to kilowatt hours where we want it. All right? But
We have to convert the megajoules to gigajoules.
yeah, the gigajoules to megajoules. You got it.
It's just 3 decimal places.
Yes, you got it. Yeah.
0036 gigajoules.
Yeah. Yeah. You're right. Maybe going too slow for you guys. You got it. So times, okay, let's do that. There's how many megajoules per gigajoule? 1,000, right? Now we could take that 3.6 megajoules per kilowatt hour and turn it upside down. It's the same number. You understand that? I went through the basics of that early in class last semester in miles per hour, figuring miles per hour or hours per mile. What did we get for an answer? Who's got it? Approximate. It's a lot of energy. I ain't a lot of room. Oh, sorry. Okay. 212,000 kilowatt hours per rail car.
Yeah, I got 211,683.
Yeah, rounded up is 212. Very well done. 200,000 is close enough, what we're looking here. We're just wanting to compare it to these other two parameters I talked about. A solar system, then that's one rail car. And I used to know how many rail cars per day went through Colstrip. I don't remember, I better not quote it. I used to know the energy Missoula uses, if half of its energy, the electricity Missoula County uses, is half its electricity comes from coal, which is approximate in Montana. How many rail cars per day that is? I just don't want to quote it. We can calculate that, but we're going to stay here with this for now. Back when I first wrote this up, I had that in there. It's way too long. Okay? But here's a visual. So that car, 212,000 kilowatt hours per day. But that's kilowatt hours or kilowatt hours per car, not per day. Kilowatt hours per car. Okay? That's how much electricity can be produced out of that rail car, given these very, very generic conditions. Okay? Who's got the next one? Anybody go there? Hope I didn't. Sometimes it won't do that.
Yeah.
So again, number 2, see if I can start way up here. Oh. Come on, dude.
Dropped to 28,000.
Oh, good. Okay. God. There it is. Let me get this thing.
Even when I get it right, I still do it 6 different ways and come up with 6 different answers.
I'm good at that too.
You just flip a coin in right.
Well, I've got 3 answers here. One of them was right, and I did all of them basically the same. I just did conversions before or after, and took the 30% before or after, and come up with a different answer. They're all in the ballpark, but there was only one that was right.
I'm going to pause the recording and stop it here for the first segment. It's all right with you folks. It's already 30-something minutes long. So let me do this.